specific heat. Specific heat was the energy required for a sample of matter. The energy required for a sample of matter for 1 gram of that matter to raise it by 1 Celsius or by 1 Kelvin. That was specific heat. So specific heat is specific for a substance. Every substance has its own specific heat. specific heat خوی هەیە واتە ژمارەی دیاریای خۆی هەیە کە چەندێکە واتە بۆ هەر 1 گرامێک لەو مادەیە بۆ 1 سلسیوس بۆی بەرزیکەینەوە چەندێک ئەنەرجی ویزەوە specific heat. جا کەمە لێرە ئاڵێن the amount of energy absorbed the total energy. This is total. Okay, total energy absorbed depends on the nature of the material. Nature of the material means the CP. So for example, if you look at this rule, this one here, Q is the energy absorbed. How much energy is needed? How much energy needed first depends on the nature of the material, means CP. Second, mass of the material. How much mass do we have? For example, if we have a lot of mass, so it needs more energy. Second, the size of temperature change, which is delta T. Okay, this is delta T, this is M. So at M كشتك بس لكن على نشانك energy معنوي. يا كمان دبنا كذا سر ناتشري مادة أو مادة شيء يعني CP كي قاعد. فقط CP كي زوري بيت يعني CP كي درجة إجمالي كي بارز بيت كاتا energy كي زورش معنوي تاكو جرمي بكين. energy كي زور ترى بيت كاتا أو energy absorb بس زور بيت. بوي علم directly proportional level أنا. إنجا mass of the material. Ataku masaki zotir betash taka zotir be. So the bigger the mass, the bigger the substance. So it needs more energy to be heated. Then the size of the temperature change. So if you want to, instead of changing the temperature by 1 Celsius or 2 Celsius, what if you change it by 10 Celsius or by 20 Celsius? Of course, you need more energy, more and more, in order to change the temperature from the low temperature to the higher temperature. Okay, so this was specific heat. Kata was specific heat. فشيء هرتاك أوش سيشتب جورتر برجمانك جورتر energy ما زادت. All right, now let's start solving questions. Practice 1. Determine the specific heat of a material if 35 grams of sample absorb 48 joule as it was heated from 293 to 313 Kelvin. So mass equals to 35 grams. 35 grams. Now, Q, on the other hand, is 48 joules. Everyone sees that joule, the specific heat is joule gram K, joule gram Celsius. So the energy always must be in joule, mass must be in grams. So as you can see, yes, this one is in gram, this one is in joule. So no problem here. What else do we have? Initial temperature is 293 Kelvin, and final temperature is 313 Kelvin. What's required? Determine specific heat. So find CP, specific heat. Okay. Now let's start solving. What do we need? If you want to write the equation, CP equals to Q divided by M, mass, times delta T. But we don't have delta T as an exact number. So what do we do? What do we do? We will use the T final and T initial. As you see, whenever you have delta is always T final minus initial. So T final minus initial temperature. T final is 313 minus 293 Kelvin. Okay. Now we will get 20K. The difference, the change is 20K equals. Now we have Q, which is 48 joule, divided by mass is 35 grams. Delta T is 20K, and the result is 0.0685. Look at the unit. Joule, as you can see, it's on top, joule, air, below it's gram and Kelvin. So that would be the unit of C. All right. Now let's solve the second question. If 980 kilojoules of energy are added to 6.2 liters. So Q again is 980 kilojoules. But as we said, you shouldn't use kilojoule, you have to convert it to joule. So it will be equal to 980,000 joules. 980,000 joules are added to 6.2 liters. Volume is 6.2 liters of water at 291 Kelvin. So this one means T initial. Why? Because it says what will the final temperature will be. So this one is T initial 291 Kelvin. Okay. Kelvin. And also CP is given. As you can see, it's water, but the CP you don't have to memorize it here. It's given. Joule, gram, K. So as you can see, Q is kilojoule. That's why the reason we have converted to joule is that the CP is in joule. Okay. But what is missing? Something is missing. One of the givens is missing.
Delta T.
Mass. Yes, delta. We have to find delta T to know T final, but something else is missing, which is mass. Then how can we find mass?
If we don't know the density too, if we knew density, we could find.
Very good. So since it's water, very good. Since it's water, 6.2 liters H2O, and the density of H2O is 1, that's why. For H2O, 1 liter means 1 kilogram, because the density is 1. The density is 1 gram for 1 milliliter, or 1 kilogram for 1 liter. That's why 6.2 liters is equal to 6.2 kilograms. All right. And we need it in grams. So mass is equal to 6.2 times 1,000 equals to 6,200 grams. Because we need mass in grams, not kilograms. That's how we get the mass also. All right. Now we'll start solving. How do we start solving? Let's see what is required. T final is required. But what do we need in order to get T final? We need T initial and delta T. So first, we'll try to find delta T in order to get T final. It's the easiest way to do. Some students integrate delta T also as T final minus T initial inside the other rule, but that will sometimes a little bit more hard, difficult. So I think it's just it's better to do it like this. All right. Now we said Q equals to Cp equals to Q over M times delta T. If you like mix the equation and change the places in order to find delta T is equal to Q over M times Cp. اگر شوێنەکان بگۆڕینەوە کوڕنە بۆی delta T بەجیا بێڵێنەوە ئاوای لێت لەسەر M قەڕەتی Cp. So delta T is equal to 980,000 joule divided by mass is 6,200 times Cp is 4.18. So the result is 37, yes, 0.8. We are going to use Kelvin or Celsius, doesn't matter. But since initial is K, let's just say K. Because it's changed, even if it's K, even if it's Celsius, it doesn't matter. It's still the same. Now we have the change. So delta T is equal to T final minus T initial. All right, T final minus T initial. We'll take this part to the other one. T delta T plus T initial will be equal to T final. Delta T is 291 plus T initial, yes, T initial is 291. Delta T is 37.8. Then T final. Then it's equal to 328.8 Kelvin. That's T final. And everyone, we can convert T final. So we can convert T final also to Celsius. This is Kelvin. All you have to do, T final also equals to 328.8 minus 273. It's 55.8, I think. 55.8 Celsius. If just in case they ask it in Celsius, always be careful. Sometimes without saying, like without being required in Celsius, one of the options will be in Celsius. Okay, everyone, do you have any questions regarding this question, regarding this practice? Okay, good. All right, now let's get to enthalpy of reaction. What does enthalpy mean? Actually, enthalpy means heat. All right, heat. Enthalpy of reaction. The H, first, let's talk about enthalpy. The H is the symbol for a quantity called enthalpy. So from now on, enthalpy means heat, and the symbol is H. But it's not practical to just talk about enthalpy as a quantity, because we have no way to directly measure the enthalpy of a system. So whenever you talk about heat, if you remember from the beginning of this section, we said we cannot directly measure energy. So heat is also energy. So we cannot measure heat. We can only measure temperature, which are two different things. Heat is caused, if you go to the definition of heat, is caused by the difference in temperature. So you can change the difference in temperature as like from specific heat like this. Q is the change. Q is the amount of energy absorbed. Is the change, is the heat absorbed. All right. So using delta, you can find the Q. You can find the Q. You can find the change in enthalpy. You can find the change in energy, but you cannot directly find the energy itself. We don't have something naming like we have this energy. The energy of something is this much. No, we don't have something like that. We only know the energy that was absorbed or released. energy بدوزینه. انرژی ماده، هیتی ماده نتونن بدوزینه. هیت گرمیه. تمپریچر به کردی پلی گرمیه. او دوشته زور جیاوازه. بۆ نمونە گەر بڵێ ئەو مادەیە چەندە گەرمە، پارچێک ئاسمان هەیە گەرمیەکی پێوەیە، با بڵێن گەرمە تا حەدێک، و تەمپریچەرەکەی زانی. هەڵێ پلەی گەرمێکی ئەوەنێ. گەرمی ئایا چەندە وزیتیە، چەندە ئەنەرژیتیە، نازانی. بەڵام ئەگەر بێت و تار ببێتەوە بۆ نە تەمپریچەرەکە بپێوین، دوای ئەو بزانین چەندە تەمپریچەرەکەی گۆڕاوە، ئەزانین چەندە ئەنەرژی ریلیز کردووە. بەڵام خۆسە سفر نەبووەوە. بڕێ ئەنەرژی هەرتیا ماوە. بڕێ ئەنەرژی هەرتیا ماوە. بۆیە مەستەن هات چێنجەکەی زانین. But only changes in delta H enthalpy, change in enthalpy can be known, can be calculated. أنا بزونيك زاني. كتشانك بابلين delta H كبس تواني بدوزينه. delta H كبس تواني بدوزينه. So delta H هل يكسر شو هاتوخي؟ If we talk about enthalpy of change, enthalpy change is the amount of energy absorbed by a system, any system, chemical, physical, anything, as heat during a process at a constant pressure. So the amount of energy change by a system in the form of heat. This energy is in the form of heat. During a process at constant pressure, it's called enthalpy change. But if it's for a reaction, we call it, this is also a definition, enthalpy of reaction is the quantity of energy transferred as heat during a chemical reaction. This one is not any system. This is special for chemical reaction. This is the definition. That's it. Quantity of energy transferred as heat during a chemical reaction. We can also call it heat of reaction. So we say enthalpy means heat, so enthalpy of reaction or heat of reaction. For something else, the enthalpy change is between maybe two substances, between two things, transfer between them. For a reaction, it's the difference between the reactant and product. How much energy is released or absorbed from the reactant when it becomes a product, when it goes to reaction. So for example, product is final. This is initial. This is initial. Basha, the final minus initial. The final in a reactant is the product. The initial in a reactant is the reactant. But we said we don't have H alone. You don't know H. These two are unknown. Are never known. We only know delta H, but just a concept. As a concept, it's product minus reactant. Concept H product minus H reactant. H بتاعتنا نزلنا بس delta H زادنا. باشا. All right. So we talked about enthalpy. We know in enthalpy H alone is unknown, but enthalpy change delta H is known. Reaction is enthalpy of reaction. Now we have two enthalpies. One of them is either, if you remember from chapter 1, one of the enthalpies can be exothermic, the other one can be endothermic. In exothermic, the delta H has negative value. Negative means release energy. Release energy. So in this case, products have, this is important, products have a lower energy than the reactant. So if for a simpler way to remember it, E in exothermic, E products are smaller than E reactants. E of reactants. All right. كواتا الإكسوثيرميكا energy product energy reactant. Energy product figure the energy reactant. شلون؟ Look at this figure. This is exothermic. The one on the left is exothermic. This is a reactant. They have a certain amount of energy. When they go react, if it's exothermic, the energy will be released. As you can see, energy will be released to the something else, and the products have a lower energy than the reactants. كواتا كورينا اللي رف فكرة كده شيء كاتك exothermic reaction ما نبي يعني الرياكتنت كا energy زور بوا product كما كواتك أنا ببنبا product أو energy زيادة شيء لكن وproduct كده نا product كده خوي تانية release يكانو فرينا درو let's form كا in the form of A and in this case delta H كده شيء negative both because product is smaller reactant is bigger. A small number minus product minus reactant. A small number minus a big number, the delta H will be negative. So, for example, in this equation, hydrogen and oxygen and H2O. In the above reaction, water will form and energy will be released explosively. The reaction is exothermic. So since energy will be released explosively, like it means a lot of energy is released. That's what it means explosively. Then the reaction is exothermic. And the energy of the product is water must be less than the energy of the reactant. So since it's exothermic, so the product is H2O, then H2O has less energy than hydrogen and oxygen. Why? Because it told you that the reaction is exothermic. Q2C, Q2 reaction exothermica. كاتك الرياكشن exothermic بيه كاتك product كمان energy كم ترى لتشار reaction تكيا. So in order to indicate this, in order to recognize exothermic reactions or any reaction, we use a type of equation called thermochemical equation. And what is this thermochemical equation? An equation that includes the quantity of energy released or absorbed as heat. Quantity of energy released or absorbed as heat during a reaction. So it's an equation that includes the quantity. We use the energy that was released or absorbed. For exothermic reaction, as you can see, it will be written in the product side. So please write this down. For exothermic, energy is written in the product side. So whenever you see energy in the product side, you don't need to write negative, positive, or anything. Just writing the energy on the product side means this energy has been released, it has been separated from the H2O. So this energy normally is inside hydrogen and oxygen. But when hydrogen and oxygen react and they form H2O, the H2O doesn't need that amount of energy. So the extra energy, the excess energy is released to the outside as heat. بجاوبه جرمية شتى الدرجة. All right. As you can see, in this reaction, it's exothermic. And we have these numbers, the coefficients. And this is 1. The coefficients in this chapter, the coefficients indicate the number of mole of the substances are very important for enthalpy calculation. So they indicate mole, amount of substance. They don't indicate, because in some other places they indicate volume. If you remember in 11th grade, chapter 4 or 5 maybe, in the beginning of chapter 5, these coefficients could indicate volume, could indicate mole, could indicate molecule. But in here, it's only mole, it's only amount. So for example, for 2 mole of H2O, in order to form 2 mole of H2O, as you can see from this explanation, for the above reaction, 483.6 kilojoule is released for what? For the formation of 2 mole H2O. Okay? But if the reaction has a different mole number, then the amount of energy released would also change by the same rate. Okay? Like this. Here is an example. So for 2 mole, it's 483.6 for 2 mole. What if we multiply the whole equation by 2? So instead of 2 mole of H2, we use 4 mole of H2. Instead of 1 mole of oxygen, we use 2 mole of oxygen. So H2O will become 4. So for formation of 4 mole H2O, what will happen to the energy? See, it has been doubled from 483 to 967.2. Le 483 قررت دوكرا. So 483.6 times 2 equals to 967.2. What if we divide it by? Same thing. So this time we divide the whole equation by 2. So you have to also divide the energy by 2. So 483.6 divided by 2 is equal to 241.8. And everyone, please, I have forgotten this one. Please write this down. 1/2. All right, everyone. Now, let's talk about enthalpy of reaction in endothermic reactions. So we talked about exothermic. Exothermic was the amount of energy released. We wrote it in the product side. What about endothermic reactions? In endothermic reactions, delta H is positive. Delta H is positive. In this case, products have a higher energy than the reactants. Energy qubit product كان مجانا بالسلبي. At this time, E of products, energy of products is bigger than energy of reactants. Okay, energy of products will be bigger than energy of reactants. As you can see from this graph here, the reactants at first have the lower energy than the product. So the reactants, when they react, they need to absorb energy. All right, absorb energy. So here it's released. In this one, absorbed. Energy is absorbed. That's why delta H will be positive. Why? So if you write delta H, the product is bigger than reactant. A bigger number minus a smaller number, the number will still become positive. Okay, positive. This time, in order to indicate in thermochemical equations, to indicate endothermic reactions, instead of writing the reaction in the product side, we can write it in the reactant side. For example, formation of water, as you can see on top, on the upper side, formation of H2O is exothermic. But the exact opposite of this reaction, which is decomposition of water. So the water is decomposing to become hydrogen and oxygen again. هالشيبونو دوباره. اگر H2O شیبو با hydrogen و oxygen جاره کتر, so it has been decomposed. If formation is exothermic, so this amount of energy is again needed to decompose it again. That's why the energy must be absorbed and it must be written in the reactant side. So this H2O must absorb this amount of energy to become hydrogen and oxygen again. As you can see from this note, the same quantity of energy released in any process must be absorbed if the reaction is reversed. For example, if A plus B, when it becomes C, it is exothermic. So if C becomes A and B again, it has to absorb the same amount of energy. So we just reverse the reaction with the energy again, and we'll have the reverse reaction. And بس به equation کو عکس کرو، اول چی من دست کرد؟ reverse reaction که من دست کرد. باشه. So these are endothermic equation. Same thing. If you multiply the energy, the reaction by a number, you have to multiply it by the energy as well. But from now on, most of the times, in many reactions, we write thermochemical equations like this. Instead of writing inside the equation, we'll write it outside of the equation. But for exothermic reactions, delta H will write negative. So instead of writing in the product side, we add negative, means release. If it's inside the equation, we don't write negative. We just write it in the product side. كواتا كورينا لا أو إنرجي أنا لكاتي أوي بابلين بجاي نوسين قال لي كوش نكانه في ماينس يجيبوا زي كانوا طاعوا بقى اكسوثيرميك بس قبل كده تي كوش نكو بيزنا ماينس يجيبوا أو كاتا لا الاكسوثيرميك for endothermic, write it in the reactant side, or when we want to write outside of the equation, delta H is positive 483.6 kilojoules. That's it. All right. Now that was the difference between exothermic reaction and endothermic reaction. Do you have any questions? Okay, very good. Now we have 4 points as a reminder. شوار خالمان هي وكو بالخروات. First one, coefficients we said before in a balanced thermochemical equation represent the number of moles of reactants and products and never the number of molecules. When in this chapter the coefficients indicate moles, دلالة شيكات دلالة مولكا دلالة هونتكا, and moles can be fractions when necessary. For example, it can be 1/2 or 3/2. Okay. Second, physical states are important. Physical state of product or reactant involved in a reaction is an important factor. Different physical states of the same substance have different enthalpies. The physical state of the product or reactant. So, for example, in the previous reaction in here, S4 is gas here, still gas, still vapor, and this amount of energy is released. But if it becomes liquid, it's different. It's different. Let me give you an example. Hydrogen and oxygen This is gas, but the H2O, 2H2O is liquid. This time delta H is not 483.6. I think it's around 500 minus 576.1. Sorry, 71.6. I think. Yes, 71.6 kilojoules. See, just by changing the physical state, the amount of energy is changed. Why? Because also changing from one state to another state also involves energy. Sometimes it's absorbed, sometimes it's released. That's why physical states is important. So different physical states of the same substance, even if it's the same substance, but different physical states have different enthalpies. كواتا عين المادة أجر physical state يتجاوزها بو كواتا enthalpy كش يتجاوزها. Enthalpy كش يتجاوزها. Good. 3. Delta H and number of mole of the substances are directly proportional. So delta H is directly proportional to the number of mole of substance. This is related to the previous note that we said. If you want to multiply a reaction by any number, then you have to multiply the delta H also by the same number. أنا قربيته reaction كات substance كان هموي كرت إجمالية كيف delta H كشبه كرت إجمالية بكي delta H كشبه كرت إجمالية بكي دابش كيف دابش بكي كاتب directly proportional. بحث عمل يريها ما بس ماشية directly proportional.
Sir, I have a question.
Yeah, sure.
For example, H2 plus O2 equals to H2O plus 575.6 kilojoules. So if we increase the mole,
yeah,
will it be like 275 or?
So it depends on how you increase them all. It depends on how you increase them all. For example, let me give you a reaction like that. Let's say, let me write the same equation. Let's say hydrogen and oxygen, 1/2 oxygen, becomes 1 H2O. Then the delta H is minus 286 point, it's 285.8. Okay, 285.8 kilojoules. Now, what about if we multiply by 2 times this equation? So it becomes 2 hydrogen plus 1 oxygen and 2 H2O. Then delta H will also be multiplied. So it will be minus 285.8 multiplied by 2. So negative 571.6 kilojoules. That's how you do it.
So we don't care about the negative sign. We should care about the amount.
Exactly. The negative tells you it's only released. The energy is released. That's what it means. Is it clear?
Yes.
Okay,
Thanks.
Welcome. All right. Now we talked about 1, 2, 3. First one, coefficient are mole. Second, physical state. Third, delta H is directly proportional to the number, just like this example. Number 4, the value of the enthalpy change is usually not significantly influenced by changing temperature. So if temperature is changed, delta H doesn't change. For example, if we do this reaction during winter time or during summertime, always nearly the same amount of energy is the difference between product and reactant. Why? Because the enthalpy change is the difference energy between product and reactant. عمليات enthalpy change هي delta H جوازها بين product والreactant. يترى قال شلونك السعر ده بيجي عين الجوازيان قال شلونك قال مش بيجي عين الجوازيان عين الانرجي برليس كات شو هذه جنب بيكو انرجي ولا قلنا حالة هذه لا كواتا value of enthalpy is usually not significantly influenced by changing temperature temperature نحكي ورد باشا all right so these were some reminders and some notes regarding the delta H regarding enthalpy change for a reaction. Now we have to study types of enthalpy. First, enthalpy of formation. We have the general enthalpy, which is delta H. Now, in two cases, we can specify the type of delta H. One of them is enthalpy of formation. What is enthalpy of formation? In order for enthalpy of formation, we have something called molar enthalpy of formation. Molar means per mole, for 1 mole. So let's look at the definition. Is the enthalpy change that occurs when 1 mole of a compound is formed from its elements in their standard state at 25 Celsius and 1 atm. It's enthalpy change that occurs when 1 mole, this is the important, of the compound is formed. So 1 mole for enthalpy formation product must be 1 mole. Got 1 mole of a compound is formed, but it's formed from what? Its elements. From its elements at 25 Celsius and 1 atm. We call that delta. We use this sign for delta H. We put this sign to indicate the standard enthalpy of a reaction. It's standard, in standard state at 25 Celsius and 1 atm. And we will add an F to become delta HF. This one is A. Okay. An example. Let me give you an example. How can we name a delta H? Let's say hydrogen and oxygen can become H2O liquid. It must be in standard state. The standard is liquid. Okay. This equation, if I want to have 1 mole, this is important. 1 mole of product must be 1 mole. Product mole. So I have to leave, if I want to balance it, I have to leave this one as 1. The product is 1. We must have only 1 mole of product, nothing else. Okay, nothing else. All right, let's balance it. We have 2 hydrogen here, 2 hydrogen here. What about oxygen? Oxygen is 1 here, that's 2 here. In these cases, how do we balance it? We balance it like this, 1/2. Because we don't want to change this one. If you change this one, it will not become formation. Okay. Now, when I want to write delta H, yes, this equation has a delta H. If it's in standard state, I can write this. But can I name it F? Can I write F here? Yes. Why? Because it's only 1 mole of H2O. That's check. Please pay attention very carefully. It is 1 mole of H2O. That's one. Second, it's formed from its elements. What are the elements of H2O? Hydrogen and oxygen. Hydrogen and oxygen. So yes, it's formed from its elements. كواتك سيركم. الإليمنت كان يوا دروز بوا كشيو تشيا هيدروجين أكسجين. إليمنت كان مهم نتشانيك. جرينغ الإليمنت بن. بلام خوي تشانيك أبي يكبت. كواتك توان شي بدامنا ما توان F بدامنا. So delta HF will be equal to minus 285.8 kilojoule. Since it's for 1 mole, so I can write per mole. Per mole. Let me give you another example. Carbon plus oxygen will become CO2. All right. We have to keep the product as 1. Yes, it is 1. CO2 formed from what? Carbon and oxygen. Carbon and oxygen. Is it balanced? Yes, it is balanced. So I will write, it has a delta H. Can I name the delta H as F? Yes, we can. Normally, for any reaction, every reaction have a delta H. But sometimes we can name them, we can put F in front of them. When can we put F in front of them? When the product is 1 mole and it's formed from its element. هذا البرودكت كمان يكمله ولا element كان يدرس بوا. باشا. وهتلاقي delta H F. For example, it's 393.5 kilojoule per mole. Kilojoule per mole. باشا.
صح؟
بله.
جت الأم
بس أيضا. إما delta H خمن الآن. delta H بعام هم الرياكشن delta H هي. بلان. أتوانين هنا delta H ناوي لبني. أتوانين هنا delta H ناوي لبني. بنمونا يك لو أنا delta H formation. لتشكاتك أبغى delta H formation. أجر هاتو. لتشكاتك أبغى delta H formation. أجر هاتو. أو delta أو reaction كلا بردم معناها. تنها يجمل product بسكا. تنها يجمل product بسكا. compounded بد يجمل به. ولا شيء شو درس بوبه. لا element كان يدرس بوبه. لا element كان. بونمونا. H2 H2O. molecule كان مولا يجمل product أو يك. لا شيء يدرس بوه. لا هيدروجين وأكسجين يدرس بوه. لا هيدروجين وأكسجين يدرس بوه. كواتا هيدروجين وأكسجين شيء element كاني H2O. كواتا من الطعام أم دلتا H أم reaction حياتي. دا بنيمو أم دلتا H بس تنها نلم دلتا H جاسية. أتوانم بيبلم دلتا H formation بو أو. لو كاتي هم جاري كوت مان. شرح. If we want to say for the formation of 1 mole of H2O, whenever you say delta HF of H2O is negative 295.8, you will understand that for the formation of H2O from its elements is this number. فتتوشي تيجي من كهركات بيطلم دلتا HF minus 285 توشي تيجي هي أو توت أو تيجي كدروزبوني يجمع فورميشني يجمع لأو لإلمنت كانيو أو إنرجي كي تيجي يعني يسمى أوانسم delta HF for H2O is equal to 285.8. This directly tells you something, and that is for the formation of 1 mole of H2O from its elements, this amount of energy is released. On energy release. Or for CO2, whenever I say delta HF of CO2 is negative 393.5 kilojoule per mole, to exert formation of 1 mole of CO2. اگر بیت یک مول CO2 دروز ببێت لە ئەلێمەنتەکانیەوە ئەلێمەنتەکانی چین کاربۆن و ئۆکسیجینە so this amount of energy is released یەکە یەکسەر تۆ تێگەی لەم شتە باشە بابا and standard enthalpies of formation are given in appendix A14 تێبڵێک بۆم کردوونەتە لە کتێبەکە تێبڵێکی تیامەش بۆم کردوونەتە مەزەمەکەوە لاپەڕەسە و حەفتە و هەنوۆیە لاپەڕەسە و حەفتە و نوێ هەموو مادەکانی تیایە enthalpy of formation enthalpy of formation سيركن area أوي هم مادەکانە for example ammonia if ammonia when it says enthalpy of formation of ammonia delta HF without explaining anything I will understand that whenever it says delta HF of ammonia is negative 45.9 what do I get I will understand that for 1 mole of ammonia NH3 if it forms from nitrogen and hydrogen then this amount of energy is released. Did you understand? So now what else do we have? Let's say ethane. Ethane is minus 83.8. What does that tell me? Ethane, when it's formed from its elements, for example, carbon and hydrogen, this 1 mole of ethane to be formed, this amount of energy is released. هر كاتك هابيس ناك هم يرجع الرياكشن قبل بنسى بس انها بتطلع دلتا اتش اف في اما اونيكا طاج تو زاني ما بس كده شيء ماشي all right what about enthalpies of elements pure elements elements in the standard states since elements are not from something else for example hydrogen alone if I want to say delta H of F of hydrogen okay I directly have to say it is 0 so this is very very important that's why I have written in bold you have to remember this one because when we solve questions you use this part so elements in the standard state are defined as having delta HF of 0 the very element element we don't know where it's come from all right and the element has it's already been created it's already present in nature that's why it's 0 بوشانكا صفر صفر all right any questions so that was enthalpy of formation we look at the product is important now stability the relation between stability and enthalpy of formation some compounds which release large amount of energy has large negative enthalpy we know yeah so if it releases energy it has a large enthalpy negative enthalpy such compounds are very very stable for example H2O since the formation of H2O is negative 285 then H2O is stable تعتبر compound formation كيف كدروز بو دلتا اتش كي نيجاتيف بو انرجيك زور ريليز بو هاتاكو ام دوز بي يعني ام خو انرجي تيانيه كما انرجيك بو اتشيا stable so it doesn't have a lot of energy because why the energy has been released so the H2O doesn't have energy the H2O as if you remember we said energy of the product is smaller than the energy of the reactant so it's very stable For example, HF of carbon dioxide, also carbon dioxide, is negative 393.5 of gas produced. Therefore, carbon dioxide is more stable than the elements from its plus form. Asígen elementەکانی چیان تیا بووە ئەنەرژیان زیاتر تیا بووە ئەسا CO2 ئەنەرژی تیان نییە بۆ لەبەرەوەی ئەنەرژی لە کاربن ئۆکسیجنەکەەوە ریلیز بوو CO2 ئەنەرژیکی کەمی هەیە. So whenever you see a compound with a delta HF of negative, you can directly say it is stable. And the higher the negative, the more the negative, the more stable. But compounds with relatively positive values of enthalpies of formation, so if delta HF is positive, or only slightly negative values, اگر تنها slightly negative يشبه, are typically unstable. But of course, the more, as you can see, or you can write this down, the more positive, the more unstable it will be. كاتا هتاكو دلتا HF كا كارين positive بس من دلتا HF مادة كا دروس سبب هتاكو positive كا زيادة بيت شبت unstable تربت قرن كاري بسرعة. What do you mean by stable and unstable? Stable means it will not react back to become the elements again. Stable بس معنى چیه؟ يعني دوباره بآسانی reaction ناگاتو ببه بشتێکی تر. یەکسەر لە خۆ نابێتەوە بە کاربن ئۆکسیجنەکە. It will not become carbon and hydrogen again. Carbon and oxygen again, sorry. Or H2O cannot become hydrogen and oxygen again easily. هلا خو نابێتەوە. So it will remain as H2O. It is stable. It will not react easily. It will not decompose easily. It will become stable. All right. But whenever it says unstable, it means that it wants to react again. It cannot stay by itself. It cannot stay just like that. It cannot stay as the compound itself. Unstable. That one For example, we have 3 examples that indicate unstable compounds. One of them is hydrogen iodide, HI. It's a colorless gas that decomposes somewhat to iodine when stored at room temperature. So hydrogen iodide, it has a delta HF of plus 26.5. It's so unstable that if you leave it HI, it will not remain as HI. It will decompose back to hydrogen and iodine. كواتا hydrogen iodide لبر delta H كدروس بوه plus بويا بأساني كبجي هالين لشوينكا شيليت يكسر أبقرته بتو با هيدروجين وآيودين. هيدروجين وآيودين. باشا. Ethane is the same thing. Acetylene. It's unstable. Please memorize these 3. HI is unstable. You don't need to memorize the numbers. Don't memorize the numbers. Just know that hydrogen iodide is unstable, ethane is unstable, and mercury fulminate is also unstable. Mercury fulminate has a very large enthalpy of formation, plus 270. That's very, very unstable. That's why its instability makes it useful as a detonator for explosives. Detonator like means for a starting of explosives. Bakari bochi waku despekarichi takina. Bo labari it's so unstable. The formation of mercury fulminate is plus 270. So when it goes back to again, it will release the energy that it has in itself. It's just like a person or a child, where it has a lot of energy, they become unstable. They move around so that they release the extra energy again. So these compounds are also the same. They have absorbed so much energy that they become unstable and they want to release it again. So these three, all you have to know, and please know this also, mercury fulminate is used as detonator for explosive. That's it. Don't memorize the numbers. So if I make a diagram like this, somewhere around here, to this side, it will be stable, but from here and to the other side, it becomes unstable. Why? If you go back to this point, compounds with relatively positive values and only slightly negative, only slightly, like maybe now -5, -4, things like that, are still considered unstable. But the more the negative, the more stable it becomes. The more positive, the more unstable it becomes.